Okay, so we've talked about the crust. We've talked about the boundary between the crust and the mantle, so that would be the moho. We've talked about the mantle, and now we've talked about the boundary between the mantle and the core. And we also know that the outer core is going to be composed of liquid, and since it was the core, then that means it's liquid iron and nickel that is circulating, and then that's what's going to be causing the Earth's magnetic field. Okay, and we also know that it's going to be a liquid because of the temperature in that region. So the temperature is high enough that iron and nickel are going to be molten. Okay, so now we want to talk about the inner core of the Earth. And the inner core is going to be solid. So how did we figure that out? How did we know that the inner core was going to be solid? So let's draw. So let's pretend that this is the outer core, and then this is the inner core. Now the S waves were stopped. So an S wave, an S earthquake wave, is going to be stopped by the outer core. But the P wave is not. So a P wave could come in, and when it gets into this liquid, it's going to change direction because it's slowing down, because P waves travel slower in liquids than they do solids. So that means it's going to, let's say, bend in this direction. And then what they found was it would bounce off of the inner core, because the inner core is solid, and that would be reflection. Now some of the P goes into here, it goes into the inner core, and again it bends, but we're not interested in that. So let's just say, for the sake of argument, that this P wave is going to be reflected off of the inner core. So then it's going to go off in this direction, so that this angle is the same as that angle, and then when it gets up to here, it's going to change direction one more time because it's being refracted. So then it's going to go off in, let's say, this direction, and then it's going to come back to the surface, so it still have to travel through the mantle, and it's going to curve as it travels through the mantle, and then it's going to get into the crust. But eventually, if you put your seismic station up here, you're going to get the this wave that originated way over here on this side of the Earth. So they were able to measure what was the depth from the mantle outer core boundary to the outer core inner core boundary by using this technique. And so now if you look at that picture there off to the side, it shows you how does the speed of P waves change as it goes through these different layers inside the Earth. Okay, so now we know the different layers of the Earth, and we know what state that they're in. Oh, by the way, why would the inner core be solid while the outer core is liquid? Because the inner core is going to be hotter, and you would expect something hotter to be in a molten condition. Well, it's a competition between pressure and temperature. So the temperature says, I want you to be a liquid. But pressure is saying, oh no you don't, you're going to be a solid, because I'm squeezing you into a solid. So that in the inner core, pressure's winning. In the outer core, temperature's winning. When you're in the mantle is solid, so pressure's winning. In the crust, pressure's winning. But what about in between? Do you remember the asthenosphere that was in between the mesosphere and the lithosphere? And we said it was plastic. Well, in that region, it's kind of a tie. So pressure saying, I want you to be a solid. Temperature saying, I want you to be a liquid. They can't make up their mind. So in the asthenosphere, it's kind of a tie. and it's partially liquid, partially solid, so it's kind of like a plastic. So those are the different layers. Those are the different rocks that are in there, the different metals that are in there, and it kind of shows how the temperature and the pressure varies inside the Earth. All right, in our next segment, we are now going to use all of this information to map the inside of the Earth. So I'll see you then.